one more minute is perfect. So welcome everyone once again to ITAMP and the workshop. And well, I see new faces again. So within 3 days we will discuss the latest advancements, the challenges and future perspectives in atomic, molecular and optical physics and its role in fast developing interdisciplinary sciences and technology. And following ideas of workshops in ITAMP, we will focus on the topic of quantum coherence and its manifestations in systems of various complexities from atomic to mesoscale. After the workshop, there will be the review volume published by World Scientific, and every participant is very welcome to submit a contribution. So we have created an exciting program, and well, it follows the major trends in the field, and we hope that it will initiate inspiring discussions. And our first speaker is Mikhail Lukin, who will speak about the new interface between quantum optics and nanoscience.
All right, so I'd like to start out by thanking the organizers for putting this kind of wonderful and diverse program together, and for invitation, of course. So I would like to actually discuss today, just as a first talk in this workshop, a little bit, give you a feeling, of this new frontier, which involves basically the interface between quantum optics or AMO physics in general and nanoscience. So, but before I go into that, so basically what we are trying to do on this frontier is to try to integrate atoms with nanoscale solid-state systems. But before I go into the details, I'd like to motivate a little bit why we are doing that. And the key goal here is to kind of try to combine the best of all worlds. That is excellent coherence and control associated with isolated atomic systems, and strong interactions, integration, and scalability, which is typically associated with solid-state systems. So just to kind of be a little bit more specific, what this kind of combination of all worlds might allow one to do is, on one hand, it might allow one to directly couple atoms or atom-like systems with tightly localized photons or phonons. And of course, if we use this tightly localized photon or phonons, you can make the interaction strength between atom and, say, single photon very, very large. And so this might enable new approaches to quantum optics and quantum information processing. At the same time, by doing this kind of work, we are really developing, control and measurement techniques at kind of, very small length scale, at sub-micron length scales. And if we are successful in that, this might open up new possibilities for sensing, metrology, and kind of other kind of near-term applications of this type of techniques at nanoscale. But realizing these ideas is actually very challenging. And the challenge is that one has to really figure out how to isolate coherent atoms either near or inside nanoscale solid-state systems. And I'll tell you a little bit about what the challenges are associated with that. But basically realizing, these ideas now requires efforts which spans a broad range of communities, physics, photonics, chemistry, nanoscience, and even biology. And I think this is really quite exciting. This kind of a new field. So I'd like to illustrate this kind of considerations with two specific examples. So in the first part of my talk, I will talk about our work involving coupling individual ultra-cold atoms with nanoscale solid-state objects, in particular with the so-called photonic crystals. And I will describe to you how we can actually realize such a coupling, and I'll also describe the first example application of these techniques. And this application will involve a single photon quantum phase switch, basically a device where a single photon can switch the phase of the atom or switch of the phase of subsequent photon beam. So, and in the second part of my talk, I will actually describe kind of a very different type of research involving quantum control of solid-state atom-like systems, and there I will actually focus specifically on application of these ideas for sensing in living cells. Okay, so let's focus on the first topic first. So the big motivation here is to try to develop efficient interface between single atoms and single photons. And this has been a long-standing goal in optical physics. This is of fundamental importance. So it's important, for example, for ultimate control of photons. But there are also many potential applications, both in quantum and actually also in classical information processing. So a couple of examples. One is this kind of idea that if you can build local quantum registers or maybe small quantum computers, you could then use this single photon, single atom interface to basically wire these kind of different nodes together by using this kind of quantum data bus. Or alternatively, one could kind of think about implementing nonlinear optics all the way down single photon level. And there, one could think about realizing the device, which somehow, unfortunately, doesn't show very well on this projector. Well, it's the first time I see this. But basically, this is a device in which single photon comes and basically flips the switch, and then this switch can control the propagation of the photon stream. So this device looks a little bit futuristic, so the projector itself does not believe this can be implemented. And yet I will tell you that we actually have implemented this kind of device in our lab. So, but this is very challenging. So the reason is that generally photons interact very weakly with single atoms, and also photons can be easily scattered and basically scattered in all sorts of directions. So photons can be easily lost. So as a result, I think it's actually fair to say that compared to, say, single ions or single neutral atoms, single optical photons are not under quite the same degree of control, at least not as these other systems. So let me talk a little bit about the physics of the single atom, single photon interface. So if you have an atom in a free space, and if you excite it, then it, of course, can emit a photon, but the photon can be emitted everywhere in all directions. So one solution to kind of to improve the control over atom-photon interaction is to place an atom in an optical cavity. And in the optical cavity, what happens is that the atom starts to preferentially interact with the certain modes of the radiation field. So this interaction can be quantified by basically this kind of single photon Rabi frequency, which basically is proportional to electric field per photon. And what happens due to this interaction is that basically the probability of emission into this mode can be enhanced. And so basically once a photon is emitted into this mode, it can leak out of the cavity in certain direction. And that way you can basically, for example, direct spontaneous emission in a well-defined mode. So the figure of merit for this kind of interaction, which we will be interested in, is something which is called cooperativity, which is basically the ratio of the emission of the atom into this desired cavity mode, gamma C, versus the free space emission in all other modes. So this is the cooperativity, and it actually can be expressed in terms of this fundamental cavity Q&D parameters is G, the free space emission gamma, and the cavity K rate kappa is G squared over kappa and gamma. And the important thing which I'd like to emphasize here is that if you take this cavity and you basically are shrinking its dimensions, so what happens is that you reduce the mode volume of the cavity and you boost the electric field per photon, and so and this cooperativity at the end is proportional to the Q of this cavity, quality of this cavity, and inversely proportional to the mode volume. So basically, we will be interested in the situation where the interaction with the cavity dominates, so C much larger than 1. But one way to achieve it is clearly to make this V as small as possible. So what the idea which we are going to pursue is to essentially try to couple an atom with the cavity which has a sub-wavelength localization of light, so with V smaller than lambda cubed. So this is basically the idea of this new approach, is to start with the light which is localized in certain structure, for example, photonic crystal, with a very small mode volume. So in particular, we'll be interested in this work in photonic crystals, which are basically waveguides, dielectric waveguides with a bunch of coils, which basically create this kind of photonic crystals. And then all what we want to do is just take single atoms and just bring it very close to this waveguide. It's very, very simple. Put the atoms in the near field of this waveguide. So, okay, so I mean, we're not the first one to really have such an idea, but it actually turns out that implementing is very, very hard. So the reason is that one needs to be able to basically confine, trap, and manipulate atom in direct proximity of the surface, basically, in direct near field of these nanophotonic systems. So in what follows, I will describe you how we actually solve this, this challenging problem. And this, in fact, we embarked upon this project in a kind of in a collaboration with Vladan Vuletic within our Center for Ultra-Cold Atoms. So basically, the idea how to do it is actually very simple, but it turns out, oftentimes this kind of simple ideas are the most powerful one. So let's consider kind of some general nanoscale solid-state system, and let's just take a focused laser beam, which we're going to use as a tweezer, and just shine this laser beam onto this small system. So what will happen in almost all situations is that basically this small object will reflect some portion of light. So it's certainly not a plane wave mirror, but there will be some reflection. And basically what will happen is that the incident tweezer light and the reflected light will interfere with each other, and then we'll create a series of kind of minima and maxima. And so, and the idea here is to essentially try to confine the atom in this most proximal kind of minimum of the trapping potential. And this first minimum will be on a scale of the order of quarter of the wavelength from this object. It can actually be somewhat closer, even depending on the phase shift of this reflected light. So, so if we can actually succeed in bringing this atom here, then we will have the atom sitting directly in the near field of this solid state object. So what you see is that the idea is actually very, very simple, but it turns out to be very powerful. And one of the things is that basically this method is really quite general. So we can trap, using this approach, we can trap atoms essentially near any object which has sufficient reflection. So, but of course, kind of implementing this idea, turned out to be kind of one of these, projects, as we discussed, for which you have to first do experiment and then ask for funding, because no one would believe that, one could do it. But actually, at the end, it really is, I must say, these are the two people, of my junior, so now my senior group members, Jeff Thompson and Tobias Tiki, who really undertook this effort, basically starting from the kind of empty lab and with the kind of very remote probability of success. I think they were really fooled in doing this project. But anyway, so basically, okay, so how is it, this is how this device actually works. So we make photonic crystal cavities out of silicon wave nitrate. And basically what we do is we first make a waveguide, we make a wire, and then we basically make holes. And these holes, they essentially constitute Bragg mirror. So one can make two of these Bragg mirrors, right? And then in between, we actually add more holes, but in these holes we modify a little bit the hole spacing. So what comes out there is that basically the light is then confined to this, if you want, defect in this photonic crystal. And so, for example, in this case, the mode volume is actually about a half of the cubic wavelength. And we can actually measure the Qs of these cavities. And actually, I must say, by now, we can make these cavities with Qs on the order of maybe half of the million. So in this talk, I will discuss, some results which we still obtain with the older generation of devices. The Q is only 15,000. But it's a pretty high Q, especially given this mode volume is very, very small. So we need to be able to tune this cavity, and the way how we tune it is by essentially heating this waveguide. But what is most important is that these cavities are radiatively damped, meaning that if once we create a photon inside this cavity, then what this photon does, it leaks out of this cavity mostly into this waveguide modes. And this is very important because at the end we want to collect this photon. So in the kind of early generation of devices, we were able to couple these photons and into the fiber with something like 60% efficiency. Actually, in the new generation, we actually can get these numbers up to 95%. So it's really kind of, the system is really a high performance system. That's what I'm trying to say. And actually what's most important is that we using the idea which I just described and which I elaborate upon, we can now bring a single atom close to this photonic crystal cavity with nearly 100% probability. So here is how it is actually done. So we basically start with the atom within a conventional magneto-optic trap, and then we just take a laser beam, focus it inside this magneto-optic trap, and wait. And then what happens is that this tweezer, this optical tweezer, can capture one atom, but it actually can capture only one atom at a time. The reason is if two atoms are captured, then they undergo something which is called light-assistant collision, and then are ejected from this trap. But so what happens is that when we trap the single atom here, we can actually look at it, and we see that we have trapped it, and then we start an experimental cycle. So experimental cycle involves first a process of Raman cooling of this atom to near its ground state. And then after that, what we do, we simply move this tweezer to basically superimpose it with our photonic crystal waveguide. And so in this case, what happens is that if the tweezer is approaching this waveguide, then there is some reflected light appears here. And basically what you see is that this new trapping potential minimum is emerging. So basically, if we start with an atom which is sufficiently cold, and basically move it, sufficiently slowly, then we can bring this atom into this nearby trapping potential with nearly 100% probability. So that's the idea of the experiment. So this is actually how the device looks like. So we start with this, we make this photonic crystal waveguide out of the silicon nitride, which is actually formed in this kind of hockey stick type shape. So Boston is kind of a hockey town, so that's why we are doing that. But basically, but there are other reasons also. But then what we do is we actually attach this the silicon nitride waveguide to the end of a tapered fiber, and so that's actually how we will be looking at the atom. So the photons will be generated in this cavity region, and then they will kind of be directed into this silicon nitride waveguide, and eventually evanescently coupled to this tapered fiber. So this coupling is can be made very, very efficient. And then in addition, of course, so what we'll do now, so we'll bring the atom close to this photonic crystal, and we will excite this atom, and then we will watch how this atom will decay. But of course, we need to tune the cavity, and the way how we tune the cavity is by basically putting what we call a heating pad, where we shine the different color of light and basically heat this structure, and by heating it, we can tune its resonance frequency. So here is the simplest experiment one can do. Is basically start with this atom and excite it with a short pulse, laser pulse, and just watch how this atom decays into this waveguide. And what we observe here is that basically within about something like 3 nanoseconds, there is substantial decay of the fluorescence, and this is to be compared with a free atom lifetime, which is actually close to 30 nanoseconds. So what you see immediately is that for the atom which sits close to this waveguide, the radiative properties are drastically modified, so the decay is actually strongly accelerated. And of course, this is essentially a manifestation of Purcell effect. And basically, if we, for example, tune this cavity away from the resonance, what we see is that this enhancement of decay diminishes, right? So basically, right here at the resonance, we have the enhancement of the decay of about something like factor of 10. And that actually allows us to extract, immediately allows us to extract these basic cavity QED parameters, this G, gamma, and kappa. And this, what I would like to point out is this value of G here. So this is a single photon Rabi frequency corresponding to electric field per photon. The value of this quantity is actually larger than gigahertz. So it's a really, really strong coupling. So we're entering this kind of condition of large cooperativity. That's good news. So what it means is that we can now really start doing interesting experiments. So as a first example of such an interesting experiment, I'd like to describe to you the realization of this so-called single photon switch, or maybe single photon transistor. And the idea of this work is actually very, very simple. So let's consider the propagation of the focused light, focused laser beam, for example, and let's think about this propagation as a kind of flow of water in a pipe. And let's consider how this kind of light beam would interact with a single atom which is sitting nearby. And let's assume that this single atom is really strongly coupled in the sense that cooperativity is very, very large. So what will happen? If you have just a single photons, traveling down this pipe, then what will happen is that this atom essentially will block the flow, right? So what this means is that if C is much larger than 1, then single photons will be almost always reflected. So that's like, you just put a plug in a pipe. But it's a kind of very peculiar type of plug because it's really a single atom. So what this means is that if you have a pair of photons incident on this guy, right, then already one photon will saturate the atomic response, and then somehow the response must be very different. So what will happen in this case, if there is a photon pair, then actually it can make it through. So what you see immediately is that the single atom is a kind of a photon sorter already, right? So it will sort single photons. You send them back. They are not allowed to come through. But for photon pairs, they can go through. So this is kind of like already gives you a little bit of a sense that this system might act as a single photon switch. Now, of course, if you would like to make something like a single photon transistor, you would like this atom to remember that it was hit by a single photon, right? So this one only responds to the perturbation locally in time. So, but if we can actually add some kind of memory, which I'll show you shortly how we can do, then one could actually see how one could make a single photon transistor, and this is this kind of, precisely this kind of device which I already showed you. So one photon hits it, and then it modifies the transmission for subsequent photons. Okay, so basically here is how we implemented it using our atoms coupled to photonic crystals. So in this case, we have a cavity, the atoms in the cavity, and it's actually a single-sided cavity. What this means is that when photon hits this cavity, it actually has no choice but to be reflected. But what happens is that if you put an atom into this cavity, what this atom does, it basically blocks the photon from entering into this cavity, and then still the photon will be reflected, but its phase will be modified depending when the atom is present in the cavity or not. So these effects can be probed with the simple interferometer. So for example, this is like a transmission and reflection of port output of this interferometer. So basically the red curve is the fringes without atom. And if you put an atom in a cavity, what you see is that basically, the phase of this fringe is shifted, and it's shifted pretty much exactly by pi, right? So this shows you that basically the presence or the absence of atom, to a leading order at least, does not, modify the reflection, but it really changes the phase. That's the main effect. Now, what we'll be doing in the following is basically just putting this interferometer phase at one specific point. For example, we fix it here. And what we'll do then, we'll basically just send in weak coherent light and monitor the photon statistics in this kind of reflected and transmitted port. And what I told you before is that this kind of system is extremely nonlinear. It should really be able to distinguish single photons from photon pairs, and actually indeed it does. So if you, for example, look at the reflected port, what you see there is that basically in the reflected port, the light which comes out is strongly anti-bunched. So it means that really single photons are directed in this reflected port. However, if now a photon pair comes, it basically hits the atom a little bit too strongly. So this photon pair will be reflected with a different phase. And what it means is it will be directed to a different output port. So and exactly what we observe. So we see that in transmission port, the light is strongly bunched. So what this really shows you immediately is that the system is extremely nonlinear. It's nonlinear at 2 photon level. So this atom kind of acts as a quantum sorter. It really sorts single photons and 2 photon states. Okay, now we would like to, of course, convert it into this kind of quantum phase switch, which I already advertised. And for that, we will use the atom with 2 internal states. So, and what you can see, of course, immediately is that, if one of the states is coupled to the mode, to the cavity mode, and the other one is not, then depending on the atomic phase, we can modify the phase of the, depending of the atomic state, we can modify the phase of the reflected light. So in other words, when the light hits this cavity and goes and is reflected, it will always be reflected, but depending on which state of the atom we will start, the phase of the reflection will be different. And as a result, of course, in an interferometer, we can direct this light into a different output port. And so what you see here is that you can observe it very, very simply, is that basically if you have two hyperfine states of atoms, if you prepare the atom in one state, then you can basically have one port which is essentially dark, and if you switch the state of the atom, then you switch the phase of the reflected light, and it will go into this output port which was already dark. And so that way you can basically route the photons by using single atoms. You can route them in one port or another, and you can actually, one atom can route many photons up to like 60 or so. Okay, so but so how does this, in order to now complete this phase switch operation, so we need to be able to use single photon to affect the state of the atom, right? So atom now can control the photon, but can single photon control the atom? So in order to do that, we can observe that the atom-photon interaction at this kind of single photon level is kind of a reciprocal process. So an atom induces a phase shift on a photon, but because it's a kind of single quantum systems, one photon should also induce a phase shift on the atom. Specifically, if you initially start out by preparing a coherent superposition of these two atomic states, and you send in a single photon, which only is resonant, for example, with this transition, upon reflection, what will happen is that the phase of this superposition will be modified, right? So like this, this photon, when interacting with atom, it undergoes this phase change, and this can be viewed as basically, in this case, as a change of an atomic phase. And what this means immediately is that you can really think about building this kind of quantum switch, where essentially what you need to do, you need to do a Ramsey experiment on these two states, prepare the coherent superposition, but then interrupt this Ramsey experiment by sending this, single photon, which will actually change the phase of the Ramsey fringe. And so, basically by controlling, by converting this superposition then into a population, you can then basically, use this phase switch to then, route the subsequent photons. So this corresponds exactly to the implementation of this device. So here is how the experiment works. So basically, this is a kind of a Ramsey experiment. So the red curve is basically just a normal Ramsey signal involving this kind of microwave transition. But the way how this Ramsey signal is read out is by sending this probe light, and then essentially, just looking, for example, at one of the output ports, right? So what we see is a very nice Ramsey signal with no gate photon applied. But then what we do afterwards, we we kind of prepare the superposition and basically interrupt this Ramsey experiment by sending a weak coherent pulse into this cavity and reflecting it from this cavity. What this reflection does, it actually modifies this Ramsey curve. And in particular, if you just look at things on average, so what you see is that the contrast of this Ramsey curve is reduced, right? So because a coherent pulse contains a certain number of photons. But if you condition on just one photon being reflected from the cavity, what we observe is that in this case, this kind of probe-on probability switches from basically being close to 0 to some large value, actually close to 70% or something like this. And so at this point, this device precisely acts as this kind of quantum switch. One single photon hitting this kind of cavity basically modifies dramatically the transmission of subsequent photons. And so this is basically, this kind of photon switch or photon transition operation. And what you kind of already can see that this is a very, very powerful kind of building block, because, for example, it might immediately enable us to actually allow one to basically, do very fast and efficient atom, photon, and also photon gates, do QND detection, and also create some entangled states. So this really opens a lot of interesting possibilities. So, and this is basically what some of these things which we are, now trying to explore. So one key point, Wolf, I would like to mention is because we can bring this atom one by one with basically nearly 100% probability, what we can easily now imagine is doing experiments where we trap multiple atoms, right? And so this way we can, for example, have atoms locally talk to each other and use this very efficient atom-photon interface to maybe kind of try to have a shot at realizing this kind of quantum networks. So also, note that in this case, one single atom really enables strong photon-photon interaction, and I think this really opens the door to really an exciting new direction where one could really do many body physics with strongly interacting photons, and actually we're exploring already some of these ideas. So, but then this kind of photon switch that this projector consistently refused to show is also a very powerful kind of element by itself, because it, for example, directly may allow us to generate some interesting and classical states, do error correction, do purification, and I think there might be some really unique applications of this type of ideas. But maybe this is a little bit too detailed here. So, how am I doing on time? 5 minutes. Okay. So this part will be very short. So let me just switch gears quickly and tell you about some totally different direction where we're actually using instead of atoms, real atoms, atom-like systems, which are basically localized impurities in solid state. So they are kind of naturally trapped atoms, which we can use for research and technology. And while one could also try to do some kind of model system type experiments, there is one key unique feature associated with this system. And this key unique feature is that they can naturally combine very tight localization all the way down to 1 or few nanometers with excellent quantum control. And actually, as such, they really open a new parameter regimes, for example, doing experiments of the time I just described, but with yet stronger coupling. But they also might enable some new unique applications. And one specific application I would like to focus on is an application to atomic sensors, basically measurement of small fields in either solid state or biological systems. So just kind of one slide, the specific system which we are using is so-called nitrogen vacancy color center on diamond. So since it already appeared on a poster of this workshop, I don't need to explain exactly what it is, but it's basically it's a color center. It's a system where a nitrogen atom basically substitutes a carbon atom in the diamond lattice, and there is the vacancy nearby. They form kind of molecular-like color center, which you can really think about nature's own trapped ions. So it's kind of like the stuff that Chris will be talking about in the next talk, but it's maybe not as good, at least as of yet, in terms of its coherence properties and quantum control. But nevertheless, so it's an optical emitter. So what this means is that basically we can just, optically in a microscope isolate individual centers. These are with a microscopy, and these are just single NV centers. So it also has non-trivial spin properties. It's spin triplet in a ground state, and you can rotate spins degree of freedom with microwave. And also, these NV centers have really long coherence time, even at room temperature. So the spin transitions can live for something like milliseconds. So then, of course, the important thing is that these NV centers can be created by just starting with pure diamond sample and bombarding it with nitrogen ions and annealing. So I think there will be a few talks in this workshop describing various aspects of this NV center physics, but what I'd like to do, I just would like to conclude my talk with just one specific kind of subject which involves application of this technique. So essentially the idea is that if you think about these guys as atoms, then of course atoms are the best for metrology, right? And if in particular what you could think about is using really a spin degree of freedom of this NV center to try to sense fields. And so this is a kind of research direction which we started a few years ago. And this actually turns out that it can be really unique sensor. So for example, you can imagine doing magnetic resonance imaging all the way down to single molecule level, where the spatial resolution of this kind of MRI is determined basically by proximity. So if you can bring NV center very close to the target, you can sense fields originating from single electrons or maybe single nucleus. But also it turns out that these ideas can be used to sense electric field and temperature and rotations. And the thing specifically that I would like to discuss is that it can really emerge as a new tool for nanosensing in biology. So this is, for example, a movie where nanocrystals containing single NV center were injected into the living cells. And so these little dots are actually single NV centers, which are existing inside the living cells. And these guys are moving around a little bit, so we can track them down. And what's amazing is that we can not only observe these NV centers, but we can also control them while they are within this kind of living cell environment. Just one example of application of this technique is a nanoscale temperature sensing. So it turns out that NV spin transition frequency depends on temperature. The reason why this is the case is that if a temperature changes, then the bonds, the orbitals of diamond stretch a little bit, and it modifies the wave function of this NV center, and as a result, it changes the spin transition resonant frequency. And the change is around 70 kilohertz per Kelvin. So for a millisecond coherence time, 70 kilohertz is a large shift. So basically, the Kelvin level temperature change will be easily observable. And so that brings up the idea of using NV center as a kind of unique thermometer. So for example, what you can think about is basically introducing this NV center somehow in a living cell, and then kind of manipulating the spin degrees of freedom. And actually turns out that you can reach millikelvin sensitivity by clever decoupling of magnetic noise. But what's most important is that this kind of small diamond particles, they can be actually very small, so they can have nanoscale detection volume and can also be biocompatible. And so this is really kind of forms the basis for this idea of using NV center for the thermometer. And actually these are Georg and Peter, the two graduate students who actually make this work. So here is how this one could actually think about this thermometer. On one hand, what you could do, you could just do the normal Ramsey experiment. And basically, in this case, what happens is that the Ramsey fringe will depend on temperature. What you can see is that if you have a kind of good coherence of the system, long T2, this will translate immediately into a very good temperature sensitivity. And for example, with a bulk diamond with a single NV center, you can sense a temperature at this kind of level of few millikelvin per root hertz. But actually, for practical measurements, we are not actually going to be using bulk diamond. We will use nanocrystals, which do not have as good temperature, as good coherence properties, but they still can be made very sensitive to temperature. And the reason is that inside these nanocrystals, you can put many NV centers. And basically, and then, at the very least, you can basically boost the signal to noise ratio by square root of the number of the NV centers inside the nanocrystals. And now what's important is that the diamond is actually an excellent thermal conductor. So that means is that if local temperature changes, then all of the NV centers will feel the same temperature. So here is finally how these measurements actually work. So what we've done is we basically introduced 100 nanometer wide nanodiamonds and also gold colloids into the living cell. And we use these gold colloids as a kind of local heaters. If we shine light on gold colloids, we can locally heat the cell. And then we can use these nanodiamonds to sense the temperature. And so here is a picture actually of the living cell. And so we can, for example, heat it in one spot and then try to measure temperature at several different spots. And what we see here is that for NV, which is really sitting close to this local heat source, then the temperature change, is induced and kind of very, very dramatically with this kind of heating laser power. But if we look, for example, at the NV, which is a little bit further away, then the temperature does not change as much. Now, to do this kind of measurement, which results in temperature changes of maybe 5 degrees, at the end of this measurement, the cell was not very happy. It was actually not alive anymore. So what we then did is basically we repeated this experiment. And what we've done is we have heated the cell very, very gently. So And then afterwards, we checked whether the cell was alive or not. So this kind of green cells here are the walls which were alive after the measurement. And what one could see here basically is that the temperature kind of changes by maybe 1 or 2 degrees at various parts of the cell, but the cell is still happy. So this kind of combination of this technique immediately allows us to, for example, control the viability of the cell, to control whether the cell is alive or dead. And the way how to do it is basically to start heating the cell and make a temperature measurement very close to this heat source. And so if now the temperature is changed by just about half of the degree, the cell is very happy. So when it's dark, it means that it's actually alive and happy. But, so now we just heat it a little bit more, heat it by, a few degrees more. And so at this point, what you see is that cell starts to fluoresce. And that means it's actually very, very unhappy. It's actually dying. So what this really, the experiment shows you that we could really do this kind of very accurate 100 nanometer scale temperature control inside the living cell. And it really opens the door for a lot of interesting possibilities. So first of all, the kind of temperature sensitivity which we can obtain is already basically a record, at least inside for the given sort of sensor site inside the living objects. But moreover, we think we can actually increase it quite a bit, and there are some kind of quantum enhanced techniques. But what's potentially most exciting is that this really opens the door for a lot of interesting applications. So, for example, one could do local control of gene expressions. One could actually try to combine with local heating technique with temperature detection to try to basically kill selectively a cancerous tissue. And this actually, in particular, very, there's a very nice synergy between this work and the work of Naomi Hallas at Rice University. And in general, of course, controlling physical and chemical processes in nanoscale is a very important tool. So I hope I convince you that, there are actually some really exciting developments at this new interface. So I talked on one hand about some kind of developments in the quantum optics, quantum information area, where we interface cold atoms and nanosized solid-state systems. And also I've told you about how we can use atom-like sensing to atom-like systems to do sensing in a biological objects. And with that, thank you very much for your attention.
Misha, for the atom trapped next to the photonic crystal, that's a red-detuned optical trap. So that's notorious for heating that. But what's the lifetime of that?
It's about a second. Yeah.
So the nano crystals and gold dots in the cell.
Yeah.
Can you move them around, or you just put them there and take what you get?
No. So what we can actually we can move them around, and the way how we can move them around is basically. So the most useful technique is basically what you do. You coat them with a certain type of thing, let's call it, which basically allows them to it allows us to target these nanocrystals and also gold colloids to certain parts of the cell. So basically, by functionalizing them and introducing them in a cell, then these particles, they find their way to well-defined parts of the cell, to mitochondria, for example, or to the cell membrane, and by that you can really do these things, completely functionally. So you can know, for example, that this nanocrystal is sitting at the right, precisely point of the cell where you want to measure this.
So how do you functionalize them? You put something on the...
Yeah, so basically what you do, you kind of fool the cell into thinking that this is a certain type of object. So, for example, so if you want to have this, thing delivered, for example, in a phagosome, right? So what you do, you put something on this on this nanocrystal, which makes the cell think that this is like a bacteria, basically, right? And then, of course, it tries to kill it, but by the way how cells kill it using, for example, some things called phagosynthesis. So they try to basically grab these, things and deliver them into certain parts of the cell. So these are fairly kind of well-known techniques. Of course, sort of applying them to these new material systems, to diamond, is actually kind of it's a new direction, but it's actually has been done, and in particular, so I have a great chemist collaborator here, kind of across the street from where I'm sitting, who actually developed these techniques.
So for this single photon, single atom transistor business, so
Yeah.
if I would like to replace it with atom-like
That's right.
solid state-based system, so what would be the challenges? How far are you from
So we're actually not too far from, so like as many of you know, we actually also have the research effort where we now make structures directly out of diamond, and actually very similar kind of structures. So the biggest challenge, and this is something where we really spent like almost 2 years of hard work, is to basically develop kind of material processing techniques to create NV centers inside these nanostructures, which also have very good coherence properties, right? So that's the key. So what you would like to do in all of these things, you would like to start with a system which is like a perfect emitter, like an ion or an atom, or maybe, something else, right? And you would like to incorporate it into this nanoscale kind of object. So basically in this work, the atoms are still free atoms. They're still very well isolated. And so even though like maybe the trap can introduce some light shifts is something we really understand. So what happens with NV center is that when you put them inside this kind of nanoscale objects, they end up being very close to surface. And as I showed you, they're very good sensors. So they start sensing everything which happens on the surface. And so basically, the things which we have been doing over the last maybe 2 years is really trying to basically develop techniques where we introduce deterministically in implanting NV centers into the structures like this, and then basically processing the surface and kind of pacifying the surface and kind of making a fabrication technique such that the surfaces are very, very smooth. It turns out to be very, very important in order to have these NV centers, have very narrow line with very good coherence properties. And actually, I must say we have succeeded in this kind of stuff. So this thing. Well, I think at the moment it's just first as a solid state, right? But then we could think about how to push this forward. That's a very good question. So it's kind of a little bit technical but so you see there are two. This NV center is a spin 1 system, right? And so it has a kind of a 0 state and plus and minus state. So we would like to do a Ramsey experiment such that we would not be sensitive to magnetic fields, right? So we do not want to be sensitive to this kind of level shift, but we want to be sensitive to this kind of level shift. And it turns out as 2 pi echo is the way to do it. No, the way how it's done is actually it's done by a by microwave, right? And basically, it of course penetrates into the cell, so it is 2.8 gigahertz. Of course, you can ask a question, whether these microwaves will hit, or this light which we shine will hit the cell. And actually, we looked at it, and sort of given a duty cycle of our experiment, this heating is irrelevant up to something like basically up to a millikelvin level, a fraction of millikelvin. So, and this is at the end, of course, will determine systematic shift, but it's a very small heating, it turns out.
Misha, I have a question about your atom on a stick experiment.
Yeah.
So you mentioned, the G value that you mentioned is astronomical,
yeah.
So 1.3 gigahertz, and the atom is sitting in this evanescent tail of the field.
That's right.
So it's varying on a very short length scale, like 100 nanometers,
That's right.
which strikes me as a huge force.
Yeah.
And so what are the mechanical effects on
No, it's a very, very interesting question, and this is something, one of the things which we are kind of trying to explore. So one of the things is that it certainly results in heating. So when we hit the atom, when we hit this kind of this cavity with the photon, right? When the atom-photon interaction takes place, right? The atom, there is this force, right? And basically what this means is that at this point where we don't have the active cooling of atom, we can only scatter around 1,000 photons with the single atom. So that's a limitation, but 1,000 already is a big number, and you might wonder, how come that we can actually scatter 1,000 atoms? 1,000 photons. It's actually an interesting question, and to be maximally honest, we do not completely yet sort of, have a foolproof answer, but actually, I believe the explanation of that is that the regime which we are operating is the regime where, so John Dowling probably kind of is an expert. So it's kind of a regime where if basically it's a kind of little bit of this quantum xenotype physics, basically. So what happens in this Duan-Kimball scheme which we are using is that when the atom is in a cavity, right, then when the photon hits a cavity, the photon never comes into the cavity, right? So when atom sits inside the cavity, its presence blocks the photon entrance into this cavity, right? It's this kind of interaction-free. It's very much goes in this direction of this interaction, free measurements and this quantum xenotype stuff. And actually, I believe that that's the reason why we can scatter so many photons.
It's an analog of Coulomb blockade.
Well, it's not a Coulomb blockade, Rydberg,
Analog.
but basically what you see is that the atom presence which basically does not allow the photon to even come in, and that's, I think, really plays a role,
Okay, Louis, very last question.
Just a quick question. Misha, along Dan's question.
Yeah.
In the earlier slide where you were showing the decay, the fluorescent decay.
Yeah.
Okay, I could be seeing things, but it looks like it was oscillating after it damped.
Well, that's, so, and, well, they're cool, but it's, of course, you should see that this is a log scale here, right? So by this time, these are like really small, things nearly decayed, so there might be something here, but what's actually, maybe what this figure really tells you is that kind of what we measure here is kind of in some way a lowest bound on our cooperativity. So what happens is if you, for example, try to fit the first few data points, you see actually much faster decay. Maybe. And I think this perhaps is related indeed to Dan's question, because what happens here is that, the atom, so the atom gets heated, right? And as a result, in some of the cases when the atom is excited, it's being close, right? And in some cases, it's being far away. And it's certain, on this measurement, I wouldn't be so sure what is happening. But for example, if we make G2 measurement, we can almost certainly, by going to long lifetimes, we could see the oscillation at trapping frequency. So, and basically, okay, so I would say at this point is that we certainly would like to gain better control of atom in this trap and, be able to cool it, to be maximally honest, this is sort of a major, at this point, it's a major. So this would improve our quality of life if we could do it. So if we could just keep the atom there for a second, even by shining photons on that, this would improve things considerably. Now, the atom, if it's just there trapped, it lives for a second. But if we start heating it with photons, it gets warm and it starts moving. It's exactly the point, yes.
What's the oscillation? What's the trap oscillation?
It's actually close. It's very high. It's a kind of at a megahertz level. Yeah. It's actually quite high. Absolute advancer, okay. So it just should work. Do you want also this? Yeah, I think it's a better laser. Yeah. Just a second.
Okay. Okay, well, thank you, Svetlana, Irina, and Christian for having me. A nice, intimate crowd, as always, here at ITAMP. So I suppose we're starting with the simple, from the bottom up, and this is certainly a bottom-up talk. I'll give the maybe the only experimental ion talk at the meeting. I'm not quite sure. But it will certainly be in the spirit of this meeting, in that we're trying to push the frontiers of complexity from the bottom up, at a single atom at a time. And I want to tell you a little bit about some of our recent work that might be termed quantum simulation of magnetism. We're building more and more complex quantum states with individual atomic ions. And I think a lot of the future of this work will follow what we just heard from Misha's group, coupling into technology, especially networking with photons and so forth. And again, this is what makes it fairly exciting kind of recently. You may think of trapped ions as being sort of the dinosaur quantum technology, and there's some truth to that. It's been around. Laser cooling was first demonstrated in ions, atomic clocks back in the old days, and so forth. But I suppose I would say the last 10 years, we've seen sort of a resurgence of this activity in the laboratory, and I guess I'd like to represent that by the list of all the groups across the world. This is probably not quite complete, but there are some 30 to 40 groups around the world now investigating trapped atomic ions as a quantum platform, of course, for quantum information sciences, but we're trying to make bigger and bigger entangled states and so forth. And what's notable is that 20 years when I got started in this field, there was one group, and only one group, doing this. So most of these groups are fairly young, and it's very exciting to sort of see different approaches, and this tells me that the field is pretty healthy, even though you might think of it as a very old atomic system. So here's a picture of a crystal from my own laboratory. In the background here, that 4-inch window, we see an ion trap. I'm not going to talk much about the technology of the traps. We had a workshop here last fall that did exactly that. But suffice to say, this is a linear RF Powell trap, and this works best with a bunch of ions in a straight line. So you might be tempted to call it a 1D system, and it certainly is in space, but I'm going to show you how we can set up interactions between these atomic ions that is not 1D at all. In fact, dimensionality takes a back seat to these long-range interactions, where the interaction graph can be quite complicated, making it quite interesting. But you'll note that for those of you that are maybe don't have too much familiarity with these ion traps, the ions are not uniformly spaced, although that's not really a big deal. They can be made uniformly spaced if we really need to. The separations are enough that we can resolve them on a standard intensified camera, and eventually individually address them with laser beams, although pretty much all the work I talk about, we're going to have global type interactions. So but before I tell you how we build the system up, let me tear it down and give you a few minutes of background on these ions and what's interesting about them. Each atom here represents a single spin 1/2 system, or a qubit, and in our experiments, these will all be identical 171 ytterbium ions, which feature, this isotope has a spin 1/2 nucleus, which makes life super easy in the laboratory. We can directly optically pump and detect these two clock states, which have only very small Zeeman shifts, meaning that without any shielding, without any heroics, we see easily coherence times of a second and longer, usually limited by our local oscillator. And all our experiments are way faster than a second. So this is an almost pristine qubit to think about doing these things. Now, I say that at the same time, we're going to be applying lasers that set up an interaction, and the lasers have classical noise on them. We're always limited by that. Okay? But the background qubit itself is very clean. Okay, so detection, again, any atomic ion worth its salt has some kind of a cycling transition. This is also true for neutral atoms. And for NVs, as Misha pointed out, you can get very strong fluorescence from them. This is absolutely essential if you want to measure these things in the end. In the ytterbium system, we exploit this cycling transition, the 1,0 to 0,0 transition. It's not exactly cycling, and I'm hiding some things. It can decay to the other 1 states, but we send in polarization that couples to all 3 transitions, and we get an effective cycling transition. And this is data showing a distribution of photons collected from a single ion prepared in the spin-up state. And in about a millisecond, we get something like 10 clicks. And this is a picture of that ion on a camera. It's bright. And when the atom is in the other state, the same light is so far away from resonance. I didn't mention the qubit frequency, 12.6 gigahertz. It's 1,000 line widths or so away from the excited state. So we see largely darkness. And the difference between these two distributions allows us to ascribe a detection efficiency, which in our lab we're at about 99%. But in the same atomic system, by simply collecting more light, and this is just with a better numerical aperture lens, this is work from Jungsang Kim's group at Duke, they realized 99% in 10 microseconds. Or if you want 3 nines, which is important if you want 100 ions, you're going to need 3 nines of a detection because you end up taking this thing to the nth power in the end. You usually do that. And again, it's very easy to get very high detection efficiencies. And I think Rainer Blatt's group has gotten 4.5 nines in their optical qubit system. Okay, so detection is very good in this. The more interesting interaction that we exploit, that will play a large part of what I want to talk about here, are off-resonant transitions that effectively set up spin-spin interactions, and I'll talk for a little bit about that. And again, there's a nice feature of the ytterbium system. The fine structure splitting is enormous. It's 100 terahertz, about a tenth of the optical frequency here. And I didn't mention the optical frequency is about 1,000 terahertz, 369 nanometers, which sounds pretty nasty, but nowadays you can actually get direct diode lasers there with 10 milliwatts of power, which is way more than we need. So this is a good thing indeed. Also related to the fact that that the number of ion trap groups has grown. The lasers get easier every year. So this off-resonant interaction, there's almost a magic wavelength where Stark shifts the differential Stark shifts from this interaction are almost 0, and there's very little spontaneous emission here. And this wavelength is about a third of the way in between here. And the best thing about ytterbium, I guess, is that this magic wavelength is a very friendly one. It's one where you can get as much power as you have money. It costs about 5 or 10,000 per watt, but you can pretty much, as much money as you have, get more power. Now, the lasers we use now are at a few watts, and as you'll see later, eventually we want this light to go very close to a silicon chip that holds the ions, so you might not want to put 100 watts at 4 Kelvin right next to a silicon chip. But notwithstanding that issue, power is not a problem here in this experiment. Okay? These are mode-lock lasers, and I won't get into the details, but they allow us to apply 2 spectral components separated by exactly 12.6 gigahertz by locking the rep rate. These are 126 comb orders apart from each other, and I won't get into the details there, but this is basically a CW source of 2 separate spectral features, if you want to think of it that way. Okay, so this off-resonant transition drives Raman, stimulated Raman processes between these 2 spin states, and this is what I want to dwell on. Now, the conventional approach to entangling ions follows the very important proposal of Ignacio Serac and Peter Zoller from a long time ago that involved driving such transitions and affecting entanglement through the motion of the ions. Again, we're modulating the Coulomb interaction here, which is super strong, and that allows us to make entanglements. And this is how it works. In Serac Zoller in 30 seconds. The idea is if you want to entangle the spin states of any 2 of these ions, you first laser cool the whole crystal to some collective ground state, say the center mass mode. We prepare in the ground state, and this is through conventional sideband laser cooling. And then we apply light on these 2 ions such that it affects a spin-dependent force. And this is easy to do with the lasers I talked about. I'll talk a little more about that in detail. But what you're ending up doing is basically setting up a sort of a dipole-dipole interaction here. The internal state of the atom becomes an electric dipole, like a p orbital. And these 2, and only these 2, will interact. Their spins will effectively interact very strongly. And if you look at the numbers, the separations are on the order of 10 or a few 10 nanometers. This turns out to have dipole moments, which are effectively very large. And if you go through the numbers, we get type kilohertz or even tens of kilohertz type couplings between the ions. And again, that's the very, very quick version. Now, Molmer and Sorensen, also Enrique Solano and collaborators, and Gerard Milburn and collaborators, showed the more general approach to what still amounts to a Serac-Zoller type process of applying a spin-dependent force. And I want to dwell on their approach, which is pretty much what everybody uses in the lab now. As important as this was, nobody uses it anymore. Nobody ever will, really, because it's much harder in the laboratory, the Serac-Zoller. Now, the spin-dependent force, I now want to talk about applying such a force globally on a collection of spins. And this will form the basis of everything I'm going to talk about from now on. The idea here is we have a bunch of ions. You can see all of a sudden the ions became PowerPoint ions, a lot easier to see here. If we apply a spin-dependent force here, the question is what types of magnetic order will emerge as the ground state here? And if you think about, so these are spin 1/2 particles, and here we have, if the spin is in the state up, then the force is also up. Easy to remember. If the spin is down, the force is down. And so under the influence of this force, if you look at the simple cases, all spins up, they'll all move up together. And the Coulomb interaction will be identical to what it was, so no change there. All spin down, they'll all move down together. And that's a similar situation. But if you think about it, this configuration, where we have alternating spins, is the ground state, because under the influence of this force, these atoms are now a little further apart. Their Coulomb energy is a little lower. So this is, in fact, the ground state of these spins under the influence of that type of a force. Things get slightly more interesting because there are two ground states. This is a spin 1/2 system. We also can have this one. You'll note also that it's kind of inhomogeneous because the ions aren't equally spaced, but those are the details of the energy gaps and so forth. But the point is we have a degeneracy of 2. This is sort of the ground state of Néel-ordered anti-ferromagnetic systems. Okay? So you can either have alternating up, down, or down, up, down, up. And in our system, it's small enough where we expect, in some cases, to see a superposition of these two, depending on how you make it, of course. But we like to think in a system this small, we don't have this thing called spontaneous symmetry breaking that condensed matter physicists hide under when they don't understand what's going on. Here, from the bottom up, spontaneous symmetry breaking shouldn't happen. And if it does, it means we have some noise or some defect that we do, maybe we don't understand. Okay, so the problem with this picture, I guess, is that this force doesn't sample Hilbert space. It doesn't flip spins. All it does is apply a shift, if you want, to energy states. So we'd like to, in addition to this force, apply a transverse magnetic field that allows the spins to precess about that field. And of course, this is now a classic system where we're interested in the relative strength of the field versus this force. And this is one version of the transverse Ising model. And we're going to be talking a lot about that. This, in some sense, the transverse Ising model is the simplest Hamiltonian that admits a quantum phase transition. And by quantum phase transition, I guess what we mean is spin temperature is 0, and the system is large enough that we're in the thermodynamic limit, whatever that means. So to me, that's just terminology. But there's lots of interesting physics in this very simple model that we want to investigate in the system. All right. So in the laboratory, we don't apply forces like this because they're much too weak. And you might think of it as comparable to getting a child moving on a swing set. You don't just push them gently and hold them there. That's not very fun. You push them on resonance, and you get a resonant enhancement, and the force can be much bigger, accumulated over time. So we do this in the laboratory, and this is a better representation of what goes on. Okay, a little complicated here, but this looks complicated, but it's not. I'll tell you that in a minute. So we applied two non-co-propagating beams. They're in practice, they're at 90 degrees. And this sets up sort of a running standing wave because these two frequencies, the frequencies of these two beams are slightly different. They're different by 2 mu. And, they're different by the hyperfine splitting, 12.6 gigahertz, plus or minus some defect mu. And so what we're doing here is we're driving stimulated Raman transitions, not just to flip the spin, that would be on the carrier at omega hyperfine, the spin 1/2 splitting, but near the upper and lower sideband simultaneously. So this not only flips spins, but it drives sideband operations. It gives a force. And when you look at the math here, again, I guess I won't dwell on this so much. Everything to the right of the laser pointer is just position, expressed as a sum of normal modes of all the ions, normal modes K and ion I. So this is just a Hamiltonian of a spin-dependent force. The spin dependence being sigma x, because we're driving on the upper and lower sidebands together. Again, this is sort of a repeat of Mulmer's idea, and also Milburn and Solano of doing quantum gates. It's very similar to the Chirac-Zoller. And here we see, well, first of all, we see that this dagger should be right there. I guess. Okay. Anyway. All right, I can hide under my experimental excuse here, but this is all pretty simple. We know what the normal mode frequencies are, and you'll notice that this Hamiltonian is stationary when this defect mu is on top of one of the sidebands. Now, we actually don't want to do that. We don't want to make phonons. We want to virtually excite the motion and adiabatically eliminate it from this Hamiltonian, and that requires that these exponents they oscillate sufficiently fast, faster than the overall strength of the force. And when we do this, it's not hard to see. By eliminating the phonon operators, we end up with a bilinear combination of these spin operators. In other words, this Ising model I talked about. And I guess again, I'm skipping lots of details here, but the important thing here is that this Ising matrix that we generate is under some amount of control by our laser, so we can tune it from the outside world. And a lot of this is not so interesting. These are the Ising coupling, the spin-spin coupling between ions I and J depends on the laser power that you have on both ions. And the recoil frequency here, which is about 20 kilohertz in ytterbium, just a number, it scales the entire problem. And then this interesting sum over all the normal modes. After all, the normal modes are mediating the interaction, so you have to sum over every normal mode, and they all have their own detuning. Okay? So there's some dispersion here. And this is a standard a Lorentzian from a off-resonant driven harmonic oscillator. These B matrices, these are the normal mode matrices, converting the ion J's position to normal mode M's amplitude. Okay? So there are signs in here. These are interesting. There's a pattern that goes with these matrices. But also, by tuning our parameter mu around, we can sort of dictate which normal modes play a big role. So for instance, if mu is right near this mode here, which is, by the way, the center of mass mode, this is the common mode. If mu is right near that, then that one dominates the sum. And we end up with a very long-range Ising interaction, infinite range. On the other hand, if we're very far tuned from all these modes, you have to sum over all of them. They're all roughly equally important, and you end up getting a dipole-dipole interaction. Now, one last thing. This is easy to understand. To apply this transverse field, we send another color into our lasers that doesn't apply a force, but it simply drives spin flips. And we phase shift this beat note compared to the others by pi over 2, and that gives us a transverse field, effectively. So here's our Ising model, and there's the transverse field. Now, you might worry that we measure along Z. We measure up and down, as I showed before, but that's very easy to do. We simply, we can apply a hard microwave common mode field to all the ions to measure along any axis. That's very easy to do, and it comes with very high fidelity. Okay, as I mentioned, so this is all theory right here, even though it looks like data. It's just simulations on a computer. Basically summing this thing up for different values of this detuning, and we're basically comparing this detuning mu with respect to the center mass mode. And when we're close to the center mass mode, the power law of this antiferromagnetic coupling is nearly zero. In other words, it's uniform. And when we tune really far away, this thing saturates at 3, 1 over r cubed, which is effectively a dipole-dipole interaction. Okay, so this simple, very quiet knob, our laser tuning, allows us to tune the range of the interaction. So that's a pretty interesting knob to have. You don't typically get something like that in a real solid. Okay, so that knob of alpha is going to play an important role. Pretty much whatever we do, we can tune alpha and see how things change. So here's the program. This is an animation borrowed from one of Seth Lloyd's early articles on quantum simulation. The idea is to prepare the spins in the ground state of some trivial Hamiltonian. In this case, it would be this transverse field. We simply polarize them to be anti-aligned with y, and they're sort of in the ground state of this paramagnetic Hamiltonian. And then we hopefully adiabatically transform the Hamiltonian from this to that. And in practice in the laboratory, we turn them both on, but we start with B really high, which does nothing because the ions are already polarized along B. And we hopefully adiabatically lower B over J. We stop at some final value, and then we simply measure every spin, and we can get every correlation function you want on every spin. Again, to do this detection, we have to rotate them all by a pi/2 pulse. I won't talk about that because it's nearly perfect. And when we initialize, we also rotate to the y direction along with the sigma x operator. Okay? Okay, so I've been talking a lot really fast. Any questions on the setup here? Yeah. Okay. All right. So we can very directly measure these correlation functions, and with the camera, we can simply show the magnetic order that emerges. So these are two calibration runs with exactly 10 spins. Here we prepared all the atoms in the state up, which fluoresces, and here they're all in the state down. They're actually there. It's just very dark because they're in the state that doesn't fluoresce. Now, we did the experiment I told you about with some range tuned by our laser, roughly 1 over distance, so it's very long-range interactions. And we tried to adiabatically lower the magnetic field to as close to 0 as we can go. And we did it 2,600 times. And every time we looked in the end at what state emerged. Okay, we can measure all 2 to the 10 probabilities. We get a histogram. With 2,600 runs, we can get a decent histogram of the probability of any configuration. And so we saw these two states about almost 20% of the time, 17% of the time. And here are 2 expected Niel ground states, staggered order. And of course, so we're not perfectly adiabatic here. That's why this number is not 100%. But it's much more than what you expect from random populations, which would be 1 out of 1,000, 2 out of 1,000. There's 2 degenerate states here. Now, if we look further upward in energy, again, we know what the energy of these states are. We can calculate them. 10 is still a small number. But here we see at about 2% each, we see single domain walls forming. These are the first excited states, where we have a defect that's close to the core, close to the middle. And then the next states, we have defects that are further away. And then this is due to the slight inhomogeneity. It's easier to have a defect further away from the middle because less spins will be upset at these two spins having the same state. Again, that's 1% each. So as I mentioned, we can plot the distribution of all 1024 states. Here they're sorted according to just their binary order. So this is all spins down, this is all spins up, and everything in between. Initially, we expect a 0.1% for every one of them, and it's, our data bears that out with the exception of a few detection errors that we understand. Like this thing here is around 128, so we have, I think, 7 spins bright, 3 dark, and we have a systematic where if one ion's bright, the next one we might diagnose it as being bright due to just errors. But this is the same data I showed before. Now this is the distribution of all the states that come out, and these two Nielord states pop out of that initial noise, if you want, and they add up to about 20%. So this plots probably a better rendition of this same distribution, but not ordering according to binary order of the spins, but according to energy. Again, we can't do this for 30 or 40 spins. It's really hard because we can't calculate the energies of all. It's very hard to calculate the ranking of all the energies, all the eigen values of a 2 to the 40th by a 2 to the 40th matrix. But 2 to the 10 by 2 to the 10 is actually not so bad. We've diagonalized it. We know all of the configurations, their energies. And here you see there's a gap near 0 energy, the ground state here at 0, and there's always a gap. And this is data for 2 different ranges of interaction. And you can see right away the longer range interaction has a smaller gap. And we expect this, again. If you have really long range interactions, the gaps get really small. Because if you have long-range interactions and you have a defect, the first excited state, yeah, it might be a defect due to a nearest neighbor, but all the ions that are far apart, they're much happier now. They're in accordance with this spin. So this is a general property of antiferromagnetic ground states, is that their gaps to the excited state get small as the range grows. But I think more interesting, you see this interesting distribution of energies. It almost looks like there's an exponential, there's a Boltzmann factor here, right? Well, where does the Boltzmann factor come from? There is no temperature. We don't have a thermal system. So this is an interesting point. Note also, some states are not coupled at all. So it can't be perfectly Boltzmann. But if you plot the cumulative distribution, integrate this from 0 to some energy, you see for both ranges, you see what looks like an exponential function. Those are the dashed lines, the best fit exponentials here. And you see the gaps, of course, from quantum mechanics. We have quantum states, and you see these steps. But it's very interesting that this seems to want to follow an exponential law. And there are some reasons for that that may have nothing to do with the Boltzmann factor, but it's a non-integrable system. And this is a very interesting topic in its own, the idea of how does a system thermalize if it's isolated. And unfortunately, we don't have the time yet to study over time some processes called pre-thermalization and then full thermalization, because of the decoherence of while the couplings are on, there's classical noise. We're still trying to fix that. But again, the qubits are in really good shape. It's more of this classical noise that we have to get control over. So here's similar data with 14 spins instead of 10. Now out of 16,000 configurations, we see, well, things are much worse now. It's much harder to make it adiabatic. Here we only have about 3% of the time we get the ground state. And again, the gaps get smaller with number. This is generally true. With a long-range interaction like this, the gaps go down like something like 1 over n to the 1/3 power. So they only go down slowly, but they're still going down. And again, everything I talk about, I guess unfortunately, we can still barely calculate on a classical computer, but that's, I think that time will end pretty soon when we punch through about 30 or 40 spins. We won't be able to calculate things, and I guess the obvious question is you shouldn't believe any of the data. And I guess that's true, but we're going to just have to see what the data tells us. Now, before I wrap up, I want to briefly talk about a few very recent experiments involving probing excited states, not just the ground state populations. We saw a little bit of that in that we showed we were trying to be adiabatic, but we were actually making excited states. This is the energy landscape of the same system, an Ising model with, I think this is only 6 spins though. So they're 2 to the 6, which is 64. Yeah, 64 states, and I think these are all of them. And the ground state are these antiferromagnetic doublets. Here's the transverse field. The excited states are, this is a doubly degenerate ferromagnetic ordered state up here. And the idea is, where do these energies lie? Well, with 6 spins, we can calculate everything. Away from 0 transverse fields, a little harder. This is sort of a spaghetti. And we've developed a new technique to do spectroscopy of this many-body state system. And let me tell you how that works. The idea is we apply this Ising model, and maybe we prepare the ground state. It doesn't matter where we start. We start somewhere, and then we apply a transverse field that's modulated in time. So this is a classic way to do spectroscopy. You simply apply a probe field, and at particular frequencies of that probe field, given that you have a non-zero matrix element, you should be able to see transitions. So for instance, all the single spin flips we should be able to derive. That's the lowest order perturbation. And we expect single spin flips to occur at certain values of this frequency. Okay? And we do this, I'm going to go a little faster here. We start in the antiferromagnetic ground state with some fidelity. With 6 ions, it's maybe 50% fidelity. And we can make transitions, basically pi pulses. They're not that great. They're not 100% fidelity. But we can walk up the ladder here. And better yet, we know what frequency that we see the transition, and we can measure. If we're looking for instance, this spin to flip here, or let's see, that spin to flip, I guess it's doubly, no, it's unique. If we start in that state and we flip the 5th out of 6 spins, that happens at a particular frequency, we can just look on the camera and wait till we see that distribution. And we can get very high signal to noise. So this is the depletion of the ground state here. We see a couple of peaks here. But more accurately, we can look for the appearance of certain states that we know should appear. These are the 3 single spin flips. And we can start from the top down. Make a ferromagnetic ground state. That's very easy to do. Just pump them all into, sort of by fiat, pump them all into one state. And measure the single spin flips from there. And we see similar data here. That was only with 6. With 12 spins, this is looking in more detail at the single spin flip, the lowest energy excitation. You can see the edge spin wants to flip from the ferromagnetic ground state. And the energy at which this single spin flips is sort of interesting. It depends on a sum of couplings. So we think of this type of spectroscopy as being a good way to characterize the Ising couplings. If you want to trust any of the data we have with 40 spins, you better trust that we're applying the Ising Hamiltonian we claim we are. And so this is actually a good way of doing this very efficiently. And I think I'm running sort of running out of time a little bit. But now, unfortunately, we can't probe all 2 to the n states. This is an exponential problem. Obviously, there's not enough bandwidth to do that. But I think here with, okay, 5 spins, set your sights low. With 5 spins, we have done exactly that, but it requires having at least 2 steps. Because if you just flip 1 spin from the ferromagnetic states and the antiferromagnetic states, you're not going to get states like, you're not going to get states that have 2 spin flips from either side. So in this case, we apply 2 separate frequencies in time, or even 3 separate frequencies, and we can pretty much map out, I'll quickly go through here, we can map out all of the entire energy landscape of this system. Down here, scaled appropriately, is the theoretical energy of our anisotropic Ising model, and here are our measurements with not so great error bars, I guess, but they're certainly consistent with our theory. And these are the 32 configurations. We see all of them. Okay? Now, probably more interesting is when we stray from zero transverse field, we can use this technique, do spectroscopy, to see to look at the gap directly, and in particular the point at which the gap is minimized. So this red line here has no fit parameters. It's based on the theory of what our Ising interaction should be, and these are the measurements sort of along the lines I showed you before of the first excited state. And finally, very quickly, we've been also looking at dynamics in the propagation of correlations in the spin chain following a quench. What do I mean by a quench? Well, we prepare what you might call an infinite temperature state, prepare all the spins, prepare every state to be equally likely, all 1024 states equally likely. This is the paramagnetic ground state. And then we don't adiabatically turn the field off, we turn it off suddenly and turn on the Ising coupling suddenly. And at 0 time, there is no entanglement, there are no correlations. They're separable. The wave function is separable here. But over time, the y-axis is time here. X-axis is ion number. Here is 11 spins. This is space. This is a space-time diagram. We should see that correlations develop over time, and there's sort of a kind of a light cone type behavior of the propagation of these correlations that was sort of described in nearest neighbor interacting systems by Lieb and Robinson long ago, and these are now in vogue in the context of long-range interactions, where this linear dependence, that is a constant velocity of the propagation, has to give way in long-range interactions to something that doesn't obey a constant velocity. It's hard to see in these are theory plots, by the way. It's hard to maybe make out that this line curves a little bit. It gets saturated. In fact, for long-range interactions, you might expect that correlations happen instantaneously, much faster than you expect from a Lieb-Robinson bound. And as you vary the range, you can see, again, 11 is still pretty small, but you might expect to want to look at the experiment right on the edge here, where the correlations form, and try to form a velocity and see what happens. So there's some recent work we've done on this in the laboratory. Notably, the group at Innsbruck, Rainer Blatt's group, concurrently is working on a very similar type system, and these 2 papers are sort of back-to-back on the archive. So this is theory with, maybe it's a little easier to see, with lots of ions, 40 ions, 41 ions, for different values of the range. And you can see, this is very interesting, when the range goes below 1, things sort of don't work anymore. And in general, when the range gets below the dimensionality of the system, you expect these Lieb-Robinson bounds to entirely break down. And again, there's lots of theory work on this, including my colleague Alexei Gorshkov. Eugene Demler here at Harvard as well has worked quite a bit on this. Also Phil Hauke at Innsbruck. So here's some data on the Ising coupling. And again, I'm going to quickly go. And what you should notice here is that the range here is getting shorter and shorter range. There's the long range. And it actually, this is a better plot of the curvature of this boundary here. That's the reciprocal plotted right here. And you see it gets more and more linear. You might not believe some of this data. The correlations are very small. But we've more recently applied a so-called XY spin model where the correlations are much stronger. And you can clearly see that this boundary gets more and more smooth as you go to shorter and shorter range. And again, I'm really running out of time, so let me wrap it up by saying that it's unfortunate that we're still at a stage where we can calculate almost everything. With systems of up to about 20 spins, we have lots of data on, and we hope very soon to push through the 20 or 30 spin border, which is sort of an accident of nature. That's the point at which you can't calculate things. It's also the point at which we're stymied in the laboratory, and it's due to a stupid thing. We can only hold about 20 ions for about 10 minutes. And what happens is the background gas causes a collision that melts the crystal, which is fine. Ions have very deep depths. And so a collision with the background gas is not deadly, but the recooling process is nonlinear. There's RF heating and so forth. And it turns out it takes about 20 minutes to get them recooled and happy when the trap stops drifting. By that time, we've had another collision. So you can see we can't take data with 20 or more spins. But we're going to go to 4 Kelvin, and we expect this 4 orders of magnitude drop in pressure will totally eliminate that problem. And so we expect in this new system to be able to hold between 20 and 100 spins and do similar things. We're not lacking for laser power. So all of our experiments should carry over in this system. And now stepping further back, I mean, we can't hope to put probably more than 50 or 100 ions in one chain. And we really need to think about scaling up in some kind of modular fashion. And there are a few ideas in the ion community of doing this. One involving these complicated electrode structures where you can clearly see this is not data. Our PowerPoint trap here, where ions in small numbers are entangled in any way you want. And then to scale up, you shuttle them around through a very complex structure. Or you turn to photonics. And this is maybe connecting to what Misha talked about. I think eventually, to make the system really big, you have to connect to optical photonics. And in this case, we have a separate project that couples atoms to single photons. Now, a few years ago, we were at about a millihertz rate of entangling over distance. We're at about 10 hertz right now. And we don't think there's any problem to get a kilohertz or above in the future. And it will largely involve better technology of the type Misha talked about, integrating with nanophotonics and so forth. And you know, there's a big community making ion traps on a chip. We have one project devoted to that, and we think that all of our work will eventually turn to that. GTRI, Georgia Tech, and Sandia in particular taking the lead. Dave Wineland's group is making their own surface traps. We got in the field a long time ago, but sort of got out when we saw what they were doing at Sandia. But this is something, you know, this is kind of a top-down approach of putting lots of ions in one place. It's sort of coming. Now, my last quick comment is a top-down approach. You have to be very careful. It's good to have a bottom-up understanding of your system before you do a top-down approach. Unfortunately, these guys didn't decide to subscribe to that type of philosophy, and many of you know about these charlatans, I call them. But many of you may also know that they finally struck gold with. I'm sure they visited Time magazine weekly for the last 10 years to try to get this, and they finally scored. But there was a typo on this cover, and it really was this. I mean, it's just unbelievable. I think in this community we should all be knowledgeable of this, of what's happening, and just be aware of it. It could affect everybody. Okay, so that's my final slide. I'll note that our group, just outside the Washington Beltway, we're very happy for the funding that we received from these guys, and the work I talked about was largely spearheaded by my senior grad student, Crystal Senko, and postdoc, Phil Risher. Thank you. I'm ready.
Do you really expect to see thermalization in these small systems? Are not the oscillations governed by finite size effect?
Well, I guess it depends how big is, because the system is I'm not sure how to think of it, because no system is truly isolated. And again, we have to, in order to implement these interactions, we have a classical laser field that will always have classical noise on it. So if you want, you can think of that as a reservoir. So there, I don't want to say that our data is showing thermalization to the laser noise, but when the system gets bigger, at some point it's not going to matter. These finite size effects will go away.
So how big? I'm just wondering, because oscillations can survive for a very long time for a small.
Right. Well, remember the interaction here is long range. It's certainly not integrable, and I think even for 30 spins, the revival time will be much longer than we can even probe. I think in theory you can go through the revival time, and again, these are I guess they're with 30 spins there are about 30 squared interactions, and they're not commensurate, and so probably depends on the first gap, and when that gets really small, the time scale is probably going to get out to many seconds.
What's the leading noise?
Pardon me?
What's the leading noise?
What's the leading source of noise in the laser?
Or in this what?
We're trying to understand. Yeah, it's a little tricky. It turns out the laser beam is focused tightly. It's a cylindrical beam. Sorry, it's sort of a cigar-shaped beam because the ions are that way. And we tightly focus in one direction. And by doing that, that means the beam is very big at some objective in the air in that direction. And we think there are air currents that change basically intensity noise at the ion. But it's not power noise from the laser. That's pretty quiet. So, we don't want to pump the whole lab down to low pressure, but maybe. So we need to work a little better on the beam delivery, but that's sort of limiting us right now. And the time scales, by the way, I don't think I mentioned it, the icing couplings are on the order of kilohertz. And our time scales at which we start to see this decoherence is several milliseconds. So fortunately, it's much slower than J over N. Because it's long range, you get to divide by N. Sorry, J times N, excuse me. So we can certainly see some dynamics and finding the ground state, but this pre-thermalization idea, I think we need to go out to 50 or 100 milliseconds in order to see that. I think that's within reach, but we'll see what happens. Thanks.
Comment and a question. The one-dimensionalizing model shows no phase transition. 2 dimensions do. Maybe you could get 2 dimensions even in your linear trap if you sort of fuzz out the vertical dimension. Think Bose condensate, right? You do get a kind of cigar one-dimensional phase transition, so maybe you guys could actually make the leap to phase transition physics without going into a lattice. It's possible.
I guess the problem is it's very hard for us to realize nearest neighbor interactions.
Very hard to what?
Very hard to realize nearest neighbor interaction, which is truly what 1D means. Now,
yeah, but if you still hold them close together, and I don't know, maybe
if they're closer together, then actually the interaction is longer range. So our interaction range is like 1 over R. So it's sort of like between 1D and something else. The graph is complicated, and so there are phase transitions. It's not 1D, that's for sure. Mm-hmm. You might argue that this is not really physical to have long-range interactions, and that's true. There are not many materials that have this type of this.
No, it's beautiful stuff.
But
my question is, when you talked about temperature, and you said, look, this is kind of like Bose condensate, kind of like a Boltzmann factor.
Yeah.
I didn't see where the temperature effects were coming from. That's just spin, and lots of degrees of freedom? What was the temperature
look, I won't claim a temperature, but again, I think Anna Maria's question that this is not an integrable system, so you have incommensurate couplings, and so there's probably very simple stat mech arguments that you should expect an exponential. They kind of always come. But I don't think the coefficient has anything to do with a real temperature in any.
It's a bit like a laser, right?
Yeah.
Sure.
Yeah, there is a lot of distribution of energies. It's always exponential. Good.
Yeah.
I guess related to the temperature question, you can also start in the highest excited state. So do you then just get an inverted temperature distribution?
Right. So in fact, some of the data I showed, we start in the ferromagnetic ground state, which we simply do by preparing the ions along the transverse field instead of anti-aligned, so that it's the highest excited state, as you say, of the transverse field, and then we do the same protocol, and we expect to see ferromagnetic coupling, and we see both states, up and
Right.
down.
But do you see then a negative temperature distribution?
You can, let's see, a negative temperature distribution. I think of it as actually inverting the sign of the Hamiltonian. I suppose you could look at it the same way. Again, I don't think about temperature in this system. I think more that the Hamiltonian is inverted, so it's now a ferromagnetic Hamiltonian.
Right, but I'm just asking, is there any reason for us to think that there's actually energy relaxation, which is causing a thermal distribution? Or is it,
Oh, I see.
it's
Is there a directionality, maybe?
It's predicated on which initial state you start with.
I see. We see no evidence of that, of a directionality, but we may not be sensitive to it either. That's an interesting question.
On the scalability, how does the Coulomb interaction limit how many ions you can put together?
Oh, good question. So in practice, I mentioned this number 50 to 100. If you pack 500 or 1,000 ions in a trap, technically you need them to be along a line. And if you don't, if you're not careful, they will buckle and form a zigzag or even more complicated three-dimensional crystals. And that's a problem because one technical issue of a Pell trap is that there's a nodal line of RF, and you want ions right there. If they're outside that nodal line, they have lots of micromotion, it's called. And so when you put lots and lots of ions in the trap, you have to weaken the trap in order to hold those guys. And if you keep weakening it, eventually you become sensitive to background fields that you don't have control over. And just in practice, this is not a fundamental limit. In practice, we think that we can do these experiments with 100, maybe somewhat more than 100 spins. But the Coulomb interaction, I mean, you're right. You put more and more in there, there's sort of a negative pressure building up in there, and you have to account for the fact that the thing can't buckle. You can't make zigzag crystals.
Is it possible to have like both ferromagnetic and ferromagnetic couplings and look at the spin class physics?
Oh, sure. In fact, there are very simple ways. By all the data I've shown, we've tuned our laser to be well outside of all the normal modes. If you go in between the normal modes, do it at your peril, because as you add spins, it gets to be pretty dense in there. But when you go in between, or maybe on both sides with two separate spectral components, you can have, say, a nearest neighbor anti-ferromagnetic coupling and a next nearest neighbor ferromagnetic coupling. So you can have it vary with range and get that kind of a frustration. Yes, there's all kinds of strange models that you can implement here. We haven't really investigated that yet. It's not so scalable, though, because most of these rely on tuning in between modes where the density gets pretty severe, and we can't slow down our experiments efficiently with this decoherence problem. So we're being pushed in by many things.
Maybe it's a little bit too detailed, but I'm wondering, when you create the effective sigma-sigma Hamiltonian by adiabatic elimination of photons, what about this, if you do usually adiabatic elimination, you will get sigma z, which is related to sort of like the Starship's effective structure.
Yes. So those are higher order, I guess?
Actually, similar orders.
Well, the lowest order, all right, so when you take the Hamiltonian I showed you and you exponentiate it to find the evolution operator, you usually get this Magnus expansion with all orders of commutators. But because the base Hamiltonian has sigma operators and just it's linear in A and A dagger, the only term that doesn't commute is A and A dagger. And they commute to a number, so all higher order commutators are gone. So you only end up with that bilinear combination.
Yeah, I'm talking about sigma-sigma instead of sigma n, sigma x. So in a sense, it's the same order, but it's different sigma.
No, the base Hamiltonian is sigma x, A. And that sigma x commutes with itself on all different ions, so you don't get a z term. Now, when you put a transverse field on, it's a sigma y, then you get other commutators. And actually, it's tricky, but it's higher order in the Lambdicki parameters, so they do get smaller. It's a mess.
Since we are a little bit behind, I have a suggestion. If we start next session at 11, if we have 15 minutes for coffee break, okay? All right, let's start.